Noise control or noise mitigation is a set of strategies to reduce noise pollution or to reduce the impact of that noise, whether outdoors or indoors. Overview: the main areas of noise mitigation or abatement are transportation noise control, architectural design, urban planning through zoning codes, and occupational noise control. Roadway noise and aircraft noise are the most pervasive sources of environmental noise. Social activities may generate noise levels that consistently affect the health of populations residing in or occupying areas, both indoor and outdoor, near entertainment venues that feature amplified sounds and music that present significant challenges for effective noise mitigation strategies. Multiple techniques have been developed to address interior sound levels, many of which are encouraged by local building codes. In the best case of project designs, planners are encouraged to work with design engineers to examine trade-offs of roadway design and architectural design. These techniques include design of exterior walls, party walls, and floor and ceiling assemblies. Moreover, there are a host of specialized means for damping reverberation from special-purpose rooms such as auditoria, concert halls, entertainment and social venues, dining areas, audio recording rooms, and meeting rooms. Many of these techniques rely upon materials science applications of constructing sound baffles or using sound-absorbing liners for interior spaces. Industrial noise control is really a subset of interior architectural control of noise, with emphasis upon specific methods of sound isolation from industrial machinery and for protection of workers at their task stations. Sound masking is the active addition of noise to reduce the annoyance of certain sounds. The opposite of soundproofing. Basic technologies. Sound insulation, prevent the transmission of noise by the introduction of a mass barrier. Common materials have high-density properties such as brick, thick glass, concrete, metal etc. Sound absorption, a porous material which acts as a noise sponge, a unregistered trademark by converting the sound energy into heat within the material. Common sound absorption materials include decoupled lead-based tiles, open cell foams and fiberglass. Vibration damping, applicable for large vibrating surfaces. The damping mechanism works by extracting the vibration energy from the thin sheet and dissipating it as heat. A common material is sound-deadened steel. Vibration isolation, prevents transmission of vibration energy from a source to a receiver by introducing a flexible element or a physical break. Common vibration isolators are springs, rubber mounts, cork etc. Roadways. Source control in roadway noise has provided little reduction in vehicle noise, except for the development of the hybrid vehicle. Nevertheless, hybrid use will need to attain a market share of roughly 50% to have a major impact on noise source reduction of city streets. Highway noise is today less affected by motor type, since the effects in higher speed are aerodynamic and tire noise related. Other contributions to reduction of noise at the source are improved tire tread designs for trucks in the 1970s, better shielding of diesel stacks in the 1980s, and local vehicle regulation of unmuffled vehicles. The most fertile areas for roadway noise mitigation are in urban planning decisions, roadway design, noise barrier design, speed control, surface pavement selection and truck restrictions. Speed control is effective since the lowest sound emissions arise from vehicles moving smoothly at 30 to 60 km per hour. Above that range, sound emissions double with each 5 miles per hour of speed. At the lowest speeds, braking and acceleration noise dominates. Selection of road surface pavement can make a difference of a factor of 2 in sound levels, for the speed regime above 30 km per hour. Quieter pavements are porous with a negative surface texture and use medium to small aggregates. The loudest pavements have a transversely grooved surface, and/or a positive surface texture and use larger aggregates. Surface friction and roadway safety are important considerations as well for pavement decisions. When designing new urban freeways or arterials, there are numerous design decisions regarding alignment and roadway geometrics. Use of a computer model to calculate sound levels has become standard practice since the early 1970s. In this way, exposure of sensitive receptors to elevated sound levels can be minimized. An analogous process exists for urban mass transit systems and other rail transportation decisions. Early examples of urban rail systems designed using this technology were Boston MBTA line expansions, San Francisco BART system expansion, Houston Metrorail system, and the Max Light Rail system in Portland, Oregon. Noise barriers can be applicable for existing or planned surface transportation projects. They are probably the single most effective weapon in retrofitting an existing roadway, and commonly can reduce adjacent land use sound levels by up to 10 decibels. A computer model is required to design the barrier since terrain, micrometeorology and other locale-specific factors make the endeavor a very complex undertaking. For example, a roadway in-cut or strong prevailing winds can produce a setting where atmospheric sound propagation is unfavorable to any noise barrier. Aircraft. As in the case of roadway noise, little progress has been made in quelling aircraft noise at the source, other than elimination of loud engine designs from the 1960s and earlier. Because of its velocity and volume, jet turbine engine exhaust noise defies reduction by any simple means. The most promising forms of aircraft noise abatement are through land planning, flight operations restrictions and residential soundproofing. Flight restrictions can take the form of preferred runway use, departure flight path and slope, and time of day restrictions. These tactics are sometimes controversial since they can impact aircraft safety, flying convenience and airline economics. In 1979, the U.S. Congress authorized the FAA to devise technology and programs to attempt to insulate homes near airports. While this obviously does not aid the exterior environment, the program has been effective for residential and school interiors. Some of the first airports at which the technology was applied were San Francisco International Airport, Seattle-Tacoma International Airport, John Wayne International Airport and San Jose International Airport in California. The underlying technology is a computer model which simulates the propagation of aircraft noise and its penetration into buildings. Variations in aircraft types, flight patterns and local meteorology can be analyzed along with benefits of alternative building retrofit strategies such as roof upgrading, window glazing improvement, fireplace baffling, caulking construction seams and other measures. The computer model allows cost-effectiveness evaluations of a host of alternative strategies. In Canada, Transport Canada prepares noise exposure forecasts for each airport, using a computer model similar to that used in U.S. residential land development is discouraged within high-impact areas identified by the forecast. In 1998, the flight paths in all of Scandinavia were changed as the new Oslo Gardermoen Airport was opened. These new paths were straighter, reducing fuel use, and disturbing fewer people. However, vociferous protests came from people near the new paths who had not been disturbed before, and they took legal action. Architectural solutions. Architectural acoustics noise control practices include interior sound reverberation reduction, interroom noise transfer mitigation and exterior building skin augmentation. In the case of construction of new apartments, condominiums, hospitals, and hotels, many states and cities have stringent building codes with requirements of acoustical analysis, in order to protect building occupants. With regard to exterior noise, the codes usually require measurement of the exterior acoustic environment in order to determine the performance standard required for exterior building skin design. The architect can work with the acoustical scientist to arrive at the best cost-effective means of creating a quiet interior. The most important elements of design of the building skin are usually glazing, perforated metal, roof material, caulking standards, chimney baffles, exterior door design, mail slots, attic ventilation ports, and mounting of through-the-wall air conditioners. Regarding sound generated inside the building, there are two principal types of transmission. Firstly, airborne sound travels through walls or floor and ceiling assemblies and can emanate from either human activities in adjacent living spaces or from mechanical noise within the building systems. Human activities might include voice, noise from amplified sound systems, or animal noise. Mechanical systems are elevator systems, boilers, refrigeration or air conditioning systems, generators and trash compactors. Aerodynamic sources include fans, pneumatics, and combustion. Noise control for aerodynamic sources include quiet air nozzles, pneumatic silencers and quiet fan technology. Since many mechanical sounds are inherently loud, the principal design element is to require the wall or ceiling assembly to meet certain performance standards, which allows considerable attenuation of the sound level reaching occupants. The second type of interior sound is called impact insulation class transmission. This effect arises not from airborne transmission, but rather from transmission of sound through the building itself. The most common perception of IIC noise is from footfall of occupants in living spaces above. Low-frequency noise is transferred easily through the ground and buildings. This type of noise is more difficult to abate, but consideration must be given to isolating the floor assembly above or hanging the lower ceiling on resilient channel. Both of the transmission effects noted above may emanate either from building occupants or from building mechanical systems such as elevators, plumbing systems or heating, ventilating and air conditioning units. In some cases it is merely necessary to specify the best available quieting technology in selecting such building hardware. In other cases shock mounting of systems to control vibration may be in order. In the case of plumbing systems there are specific protocols developed, especially for water supply lines, to create isolation clamping of pipes within building walls. In the case of central air systems, it is important to baffle any ducts that could transmit sound between different building areas. Designing special-purpose rooms has more exotic challenges, since these rooms may have requirements for unusual features such as concert performance, sound studio recording, lecture halls. In these cases reverberation and reflection must be analyzed in order to not only quiet the rooms, but to prevent echo effects from occurring. In these situations special sound baffles and sound-absorptive lining materials may be specified to dampen unwanted effects. Materials acoustical wall and ceiling panels can be constructed of many different materials and finishes. The ideal acoustical panels are those without a face or finish material that interferes with the acoustical infill or substrate. Fabric-covered panels are one way to maximize the acoustical absorption. The finish material is used to cover over the acoustical substrate. Mineral fiber board, or MICOR, is a commonly used acoustical substrate. Finish materials often consist of fabric, wood or metal. Fabric can be wrapped around substrates to create what is referred to as a prefabricated panel if laid onto a wall, and require no modifications. Such fabrics are generally acoustically transparent, meaning that they do not impede a sound wave. Prefabricated panels are limited to the size of the subbers on-site acoustical wall panels. This is constructed by framing the perimeter track into shape, infilling the acoustical substrate and then stretching and tucking the fabric into the perimeter frame system. On-site wall panels can be constructed to work around door frames, baseboard, or any other intrusion. Large panels can be created on walls and ceilings with this method. Double-glazed and thicker windows can also prevent sound transmission from the outdoors. Industrial. This situation classically is thought to involve primarily manufacturing settings where industrial machinery produces intense sound levels, not uncommonly in the 75 to 85 decibel range. While this circumstance is the most dramatic, there are many other office-type environments where sound levels may lie in the range of 70 to 75 decibels, entirely composed of office equipment, music, public address systems, and even exterior noise intrusion. The latter environments can also produce noise health effects provided that exposures are long-term. In the case of industrial equipment, the most common techniques for noise protection of workers consist of shock mounting source equipment, creation of acrylic glass or other solid barriers, and provision of ear protection equipment. In certain cases the machinery itself can be redesigned to operate in a manner less prone to produce grating, grinding, frictional, or other motions that induce sound emissions. In recent years, Be-Quiet programs and initiatives have arisen in an effort to combat occupational noise exposures. These programs promote the purchase of quieter tools and equipment and encourage manufacturers to design quieter equipment. In the case of more conventional office environments, the techniques in architectural acoustics discussed above may apply. Other solutions may involve researching the quietest models of office equipment, particularly printers and photocopy machines. Impact printers and other equipment were often fitted with acoustic hoods, enclosures to reduce emitted noise. One source of annoying, if not loud, sound level emissions are lighting fixtures. These fixtures can be retrofitted or analyzed to see whether over-illumination is present, a common office environment issue. If over-illumination is occurring, delamping or reduced light bank usage may apply. Commercial reductions in cost of technology have allowed noise control technology to be used not only in performance facilities and recording studios, but also in noise-sensitive small businesses such as restaurants. Acoustically absorbent materials such as fiberglass duct liner, wood fiber panels and recycled denim jeans serve as artwork-bearing canvases in environments in which aesthetics are important. Using a combination of sound absorption materials, arrays of microphones and speakers, and a digital processor, a restaurant operator can use a tablet computer to selectively control noise levels at different places in the restaurant. The microphone arrays pick up sound and send it to the digital processor, which controls the speakers to output sound signals on command. Urban planning, communities may use zoning codes to isolate noisy urban activities from areas that should be protected from such unhealthy exposures and to establish noise standards in areas that may not be conducive to such isolation strategies. Mixed-use areas present especially difficult conflicts that require special attention to the need to protect people from the harmful effects of noise pollution. Noise is generally one consideration in an environmental impact statement, if applicable. See also, acoustic quieting, active noise control, by quiet, noise reduction coefficient, noise regulation, noise, vibration, and harshness, vibration isolation, general, noise pollution, health effects from noise. References. External links, Addressing Wind Turbine Noise, Acoustical Society of America, American Institute of Architects, National Council of Acoustical Consultants, Business and Institutional Furniture Manufacturers Association, Cambridge Sound Management, City of Melbourne City Sounds Guide to Urban Residential Design, Noise Abatement Society, Noise Control Case Studies, Industrial Noise Control Case Studies, Multiple Sound Isolation Research Articles for Beginners, NIOSH by Quiet Topic page.